Who's Who. And with that, I'd like to introduce the next talk by Chris Hatton. Chris did his PhD in 1978 at UCT on eclogite from Roberts Victor Mine. He then did a postdoc at Smithsonian Institution. He returned to South Africa and joined the Bushveld Research Unit at the Institute for Geological Research on the Bushveld Complex at the University of Pretoria. In 1989, he joined De Beers and got into diamonds again. He's been involved with Shango Solutions, MSA Group. He's currently on working for the Council for Geoscience and has been secretary of the SACS committee, South African Committee for Stratigraphy. He has been doing some mapping in the Bushveld complex. He's also has been for a number of years the editor of the GSSA Geo Bulletin, and he's now head of the Geoheritage Division of the GSSA. So Chris, with that, take over and deliver the goods.
Thanks, Craig. Can you see me?
Yes.
We can.
Great, thank you. Okay, so welcome everybody. This is incredibly convenient sitting here next to the sea and giving a talk on the Bushveld. So I'm talking about magmatic water as a control on chrome, PGE and vanadium mineralisation in the Bushveld complex. Okay, this is the CGS disclaimer. This is the introduction. So for a long time, a popular idea was that the Bushveld was the product of, with the chromatite layers, a mixing between U and A-type magmas. This was a model of Irvin based on work of Halmer and Sharp. The problem, one of the problems was that the critical and lower zone magmas both seem to be U-type. And that was argued, well, Cameron argued that long ago. Meyer followed up on that, and that's a problem for the magma mixing hypothesis. Another problem is that the marginal zone is not necessarily representative of the layered sweet magmas. And that Cawthorne picked that up early on. Michiel de Kock is supporting this with paleomag results. So we need a new model. Magma mixing doesn't seem to be the way to produce chromatite layers. And then another aspect, besides what Wolf has just pointed out, is the evidence for massive fluid flow in the Bushveld. And there's also this fact that hafnium isotopes limit the number of components that can be present in the Bushveld. Crystal contamination of the source is unlikely, but the Platreef, I think, shows you what's happening when you have contamination. But that is late stage contamination. The source of the Bushveld magmas are very simple or very limited. There can only be a few components. Okay, so what I'm going to try and say today is that water suppresses silicate crystallization, but not spinel. So water can allow you to crystallize spinel alone. The Bushveld magmas are hydrous, and Wolf pointed out that Boudreau and Mattez pointed that out long ago, but people didn't believe it, but I think it does seem to be the case. And the important thing is that water solubility depends on pressure strongly. So as soon as the magma comes into the chamber at depths of somewhere between 3 to 6 kilometers depth, the pressure is now dropped dramatically and the water leaves the chamber. But as it leaves the chamber, it initiates chromatite or magnetite crystallization. And the source of the water is actually primordial. It's primordial magmatic. The sulfur is crustal, so it's got this sulfur isotope signature that says it must be Archean or older, and the most likely time is that it's generated at a surface at 3.7 billion years ago. And then, of course, the PGEs are scavenged from the U-type magma by this sulfur. Okay, so Nicholson and Matez pointed out long ago that high water contents cause chromite spinel to crystallize alone. So as the water pressure goes up, the liquidus solidus of silicates drops dramatically, whereas spinels, the curve, the stability curve is not affected as much. So if you increase the water content, you'll go from crystallizing silicates to crystallizing spinel. The same thing happens with magnetite, but at lower temperatures. Water drops as the water content goes up. The silicate crystallization temperature drops dramatically, whereas that of spinel is relatively unchanged. So at very high water contents for magnetite, you'll crystallize magnetite alone. The problem here is that you need very high water content, but I think we can see that this is actually possible, that you can have these very high water contents building up in the Bushveld magmas. So in general, there's been a shift from this view that all magmas have very low water content. Morb has got very, very low water content. But Morb is not the rule. Morb is the exception. All other magmas have got 1, 2, 3, 4, 5, 6%. The Karoo, 1 to 2% water. So there's this, the upper mantle produces relatively dry magmas, but these lips that are coming from the lower mantle, they all have variable amounts of water, up to very, very high contents of water. And if you have water to start with, if you get, by the time you get to the upper zone magmas, here Grant Cawthorne and later Cetera and Vertongeren have estimated how much the rare earths are enriched in the upper zone above the peroxenite marker, and it's a very high factor. So the upper zone magma is highly fractionated. So if there's a little bit of water to start with, by the time you get to the upper zone, you're going to have very, very high water content. Now, Steve Barnes and many other people have said, the Bushveld is dry, and that's the case for, most magmas. They look dry, but the reason is that at 40 kilometers, you can hold a very large amount of water. This is an extreme example from one study. You're looking at something like 20% water in the magma at the base of the crust at 40 kilometers. And there's other estimates, but the important point is that at very high, at high pressure, you can hold a lot of water. When you get down to 3 kilometers depth, the water content drops dramatically. And this is a recent study looking at a flood basalt. And here, at 13 kilobars at pressure at the base of the crust, you're looking at 4% water, that as the pressure drops off, the water content doesn't change, but as you come towards surface, the water is all exsolved. So at low pressure, all the magma has exsolved all the water is exsolved from the magma. But so you don't see all the water that was in the magma, like you would expect to see hydrous minerals in the late stages. You don't see that because by the time you have late stage crystallization, all the water has escaped. So this is as Wolf mentioned, Boudreau was among the first to point this out, to suggest this, that Bushveld magmas were wet. And his estimate based on the chlorine-fluorine ratio was that the Bushveld and the still water contained more than 1% water. And the hydrogen, the deuterium isotopes were hovering round about between -60 and then lighter down to -90. Boudreau said, the Bushveld overlaps with Boninit Island and it's different from Morb, but that the estimate of what the deuterium per mole value of Morb has changed. The study by Clog has shown that Morb actually has a delta deuterium per mole value of -60, not -80. And if you look at the Marinsky Reef, the peak in the Marinsky Reef is close to -60. So the Marinsky Reef is looking just like the new value for Morb. And in the study by Matez, he shows that the Marinsky Reef clusters around about -60, and if you have magmatic loss of water, that will then change your deuterium values. The Marinsky Reef looks like primordial deuterium ratios. So the peak for this is the Marinsky Reef at -60. Degassing drives the value away from that. Now the sulfur isotopes in the Marinsky Reef and in the UG2 and in the main zone are incredibly restricted. This is a study by Peniston Dorland and others. This very tight cluster, but this very tight cluster is actually extraordinarily tight. So the Platreef, this is the Marinsky Reef, is actually this little star. The Platreef, it does show signs of contamination. But when you look at the Marinsky Reef values compared to the sulfur isotopes values in the upper crust, it's this very, very small little dot. So the Platreef shows crustal contamination, but the Marinsky Reef is uncontaminated. So the message is that the Marinsky Reef is uncontaminated in respect to sulfur. The Marinsky Reef hydrogen values are representative of the original hydrogen isotope values in the Bushveld. Okay, so I now just want to have a look at the middle group of chromatite layers and see how this model of degassing can explain these extraordinary differences between the chromatite layers north and south of the Steelpoort Fault. So if you look at the MG2 chromatite in these mining outcrops, which are now being exposed all over the Steelpoort Valley, the MG2 chromatite layer is 1 meter thick. So it's sitting at the boundary between the lower critical zone and the upper critical zone. If you go to the Jachtlist Winterveld section or north of the Steelpoort Fault, you can see that same boundary between the lower critical zone and the upper critical zone. And there you have a chromatite stringer that's just 1.5 millimeters. So you've got this extraordinary difference of the middle group chromatite layers changing dramatically north and south of the Steelpoort Fault. South of the Steelpoort Fault, you see the same thing everywhere. North of the Steelpoort Fault, you see the same thing everywhere. So with the stratigraphy is incredibly constant. You hit the Steelpoort Fault and the stratigraphy changes dramatically. To the south, you've got this different stratigraphy that's the same. So the same thing applies to the lower group of chromatite layers, but in reverse. South of the Steelpoort Fault, there are no lower group chromatite layers. To the north, you've got the LG6 being mined along for 80 kilometers of strike almost. So how did this happen? The Steelpoort Fault marks a boundary, and so to the north of the Steelpoort Fault, your lower critical zone and your lower zone magmas were emplaced. Then the magma spread southward to the south of the Steelpoort Fault. So because chromatite layers, according to this water exsolution model, they form immediately upon emplacement of a new pulse of magma. A new pulse of magma comes in, the water degasses, chromatite settles. So when the magma north of the Steelpoort Fault has produced the LG chromatite layer, the lower group chromatite layers. When it goes south, it's degassed, and you don't get chromatite layers in the lower group to the south of the Steelpoort Fault. For the upper critical zone, the magma comes in south of the Steelpoort Fault. You produce the middle group chromatite layers, then the degassed magma goes northward and produces hardly any chromatite layers to the north of the Steelpoort Fault. So, because chromatite layers form during degassing of magma, the lower group of chromatite layers form during gassing of magma north of the Steelpoort Fault. The degassed magma then spreads south, producing only chromatite stringers or poorly developed layers. The middle group chromatite layers form during degassing of magma south of the fault, and then the degassed magma spread to the north, producing only chromatite stringers or poorly developed layers in the middle group. So this degassing model can explain this major mystery of the Bushveld complex, this dramatic difference in the chromatite layers north and south of the Steelpoort Fault. And this model can be extended to the to the western bushveld, where you've got the Spraitfontein upfold, and you've got the similar dramatic change in stratigraphy, north and south of the structure. Okay, so that's essentially the story. Water degassing is a better model to produce chromatite layers. So the question then is, where does this water come from? And there's this big debate is how much water is in the core. And in this review, they said that the core contains about 12 earth oceans in the core. They looked at the other ones. So they're saying the core contains huge amounts of water, 12 times the amount of water that's in the ocean. But actually, there's old studies which have been backed up lately that there's even more water in the core. So this diagram shows the volume of the water in the oceans. That's all the water in the oceans. To explain the density deficit in the core, that can be explained by something like 1 weight% hydrogen, which corresponds to about something between 60 and 120 times the mass of the ocean. So in other words, the core contains about 100 times more water than is in the oceans. So as the core cools, it expels water, and it's this water that drives lower mantle magmatism. This is the early study by Foucault and others, where early on they estimated the amount of hydrogen in the core. For every 100 atoms of iron, you've got 36 atoms of hydrogen, giving you this result of about 100 ocean masses of water in the core. And this has been confirmed experimentally. Hydrogen dissolves in iron. So there's no way to stop hydrogen dissolving in iron. So when the Earth was forming, there's no way to stop it sucking up huge amounts of hydrogen and water. So the water is in the bushveld is primary magmatic. That primary magmatic comes from the core. So then the water comes from the core. Where does the sulfur come from? The sulfur is crustal. The sulfur isotope results of Pennis and Dorland demonstrate without doubt that the sulfur comes from the crust. Jock Harmer showed that the bushveld fits the Stacey-Kramer model very, very well. And that model says that at 3.7 billion years ago, there was this major change in the uranium-lead ratio of the source of magmas at surface. So that major change at 3.7 could be related to the formation of this 3.7 billion year crust, which during this catastrophic event at 3.7 forms at surface and could then sink to the core mantle boundary. So the sulfur comes from the crust in this major event at 3.7 and goes down to the core mantle boundary. And so Jock's results show that you've got this high uranium lead component in the main zone, which is your A-type component, your basaltic component, and your lower uranium lead ratios in the lower zone, which is your U-type component, the peridotite component. So the bushveld essentially is a product of peridotite and basalt, and the other component is water. So essentially the bushveld is just three components: a peritic component, a basaltic component, and a water component that fluxes the whole thing. So the new model, which is essentially following on from Nicholson and Matez, is that high water contents suppress silicate crystallization, but not spinel. So if you can get high water, you can cause spinel to crystallize on its own, and that's where you're going to get the chrome deposits in the chromatite layers, or the vanadium deposits in the magnetite layers. And the bushveld magmas are hydrous. And it's not just the bushveld, all magmas from the lower mantle are hydrous. And because water solubility is strongly dependent on pressure, this has been known from Burnham's work long ago, so at high pressure you can dissolve a lot of water in a magma. When you come to shallow levels into the bushveld magma chamber, the water exsolves. So immediately after the emplacement of the magma, the water exsolves, the water content goes up, you crystallize chromatite, you crystallize magnetite, the exsolution of water lowering that stops silicate from crystallizing will allow sulfides as well to crystallize on their own. So this very simple mechanism can explain how just by water suppresses silicates and it allows spinels and sulfide to crystallize on its own. And that simple mechanism can explain the PGEs, the chrome, and the vanadium. The water comes from its periodic release from the core as it cools. It expels water that drives lower mantle magmatism. The sulfur definitely comes from the crust, and the simplest way of explaining that is that sulfur formed in basaltic crust that was generated at the time of this major Stacey-Kramers transition at 3.7 billion years. And then, of course, the PGEs come from the U-type magma. The sulfur is brought in by the main zone magma that ponds below the resident U-type magma, and then scavenges the PGs from the U-type magma. And those density calculations have been done most recently by Seabrook and Crustal. So thank you. And yeah, I'd like to thank Wolf for some thought-provoking comments in the last few months. Thank you.
Thank you very much, Chris. That was a great talk. I'm sure there's going to be some questions and comments. So I'll open the floor to that. Raise your hand, or George Henry, you go ahead. Unmute your mic.
Thank you, Chris, for an interesting talk. Chris, you keep on mentioning water in the core of the Earth. In what form does the water exist? Because you have hydrogen and you have oxygen. Now, do you have hydrogen H2 and O2 separate, or is it some sort of high pressure form of H2O? So this is not quite clear as to how you can actually preserve H2O in the core.
Right. There's a whole lot of recent results coming out in the last couple of years. The water in the core is in the form of FeO2H. It's basically a high pressure mineral, which they've called phase P. So this phase P mineral is stable is stable in the core, and it crystallizes at the core mantle boundary. It's not stable in the lower mantle, so it then breaks down as it leaves the core. But yeah, I can send you the references to the recent work that's been done on phase P. So yeah, now that's a very important point, is that it's not sitting as water. It's associated with iron in this mineral phase P, which it's called phase P because it has a pyrite structure. But there's been a flurry of recent work, with these incredible experiments at high pressure that stabilize these minerals. And yeah, so phase P is the host of the water in the core.
But Chris, at what stage as the water leaves the core, does it become H2O? It has to form H2O somewhere on its way up towards the crust.
It essentially becomes a melt phase because it's unstable. Phase P crystallizes at the core mantle boundary, breaks down, becomes unstable, and forms part of a melt phase. And that melt phase is what allows plumes to ascend. And then below 1,800 kilometers depth, there's another phase transformation, and it's essentially a high pressure form of goethite. So it's basically rust down to 1,800 kilometers is the host for water. It's unstable between 1,800 and 2,800 kilometers. And then phase P is stable in the core. So it's quite a complicated situation. But yeah.
Thank you.
Wolfgang, you have your hand up. Can you unmute yourself? Okay.
Can you hear me now?
We can hear you.
Yeah.
Okay, so Chris, just one quick question. Your model essentially argues that the magnetite seams and the chromatite seams form during and after magma replenishment, right?
Yes.
So Grant Cawthorne a couple of year ago in a paper, I can't remember, was it with Lou maybe, with Lou Ashworth, they looked at upper zone magnetite seams and did a sort of a fairly thorough examination of magnetite seams and anorthosites, in fact, and did a fairly thorough examination of plagioclase compositions across the upper zone and notably across below and above these seams. And they found that there is no change whatsoever, apparently, if I remember correctly, in the composition of plagioclase from below and above the seams. And from that, they concluded that the magnetite seams cannot have formed from new magma replenishments because you would expect a change in composition of the plagioclase then above the seams.
Yeah, I don't think that you would expect a change in composition after every pulse of magma. There's very minor perturbations, and I think as you and Hugh Eels pointed out long ago, the changes in composition across the layer are not that systematic, but essentially that you're not emplacing a primitive magma. The magma is evolving in the magma. The main magma chamber is at the base of the crust at 40 kilometers, and it's that's fractionating, and you're getting pulses which are probably, pulses which produce silts of the order of 500 meters thick, are being tapped from this lower from the subcrustal magma chamber. So the phase relations are not controlled in the chamber. They're more controlled by the subcrustal magma chamber. So I think this lack of major changes across magnetite layers is not a conclusive argument against emplacement of new magma. I think, you know, in one aspect of this Mongol story is that the Bushveld, you know, the Bushveld magma chamber was never an 8-kilometer pile of magma. It was probably a magma chamber of the order of 500 meters thick, which was being fed from the lower crust, and the magmas were spreading southward. So the Bushveld magma chamber is a sort of is an open system, and that's why you don't see these dramatic shifts, you know, at each and every chromatite layer or at each and every magnetite layer.
Thank you.
Chris, thank you very much. I'll stop the questioning there. In the interest of time, we're running a little bit behind, but I think